Now that we've looked at the t confidence interval, let's take a look at the t-test. We had a z-test before, and we used that when we did not know the mean of our population, but we did know the standard deviation of the population. We have a t-test, and we're going to do very similar things to what we did before, but this is where we don't know the mean of the population and we don't know the standard deviation of the population. We've already talked about the null hypothesis and alternative hypothesis, the one-sided test versus a two-sided test, what your significance level is, when to reject and fail to reject your null hypothesis. In the last video, you saw how to calculate your t-statistic and how to get your degrees of freedom. So let's take a look at this here. Now, just to review, if you're dealing with a one-tailed test where you're greater than for your alternative hypothesis, you're looking at what's in the upper tail. If you're looking at a one-tailed test where it's less than, you're looking at what's in the lower tail. If you're dealing with doing this by hand and you have a two-tailed test, remember you got to take what's in your lower tail and just double it to get both. But normally we're going to be doing this with our calculator, and that already doubles it for us. Now, how do we do this? Well, suppose you had a t-value of 2.7. And we had degrees of 9 for our freedom. So we go across on our row of 9 until we get 2.7. You'll realize that 2.7 doesn't show up. But 2.7 is in between these two values right here. Now, if you're dealing with a one-tail test or a two-tail test, you go straight from there and you go straight down until you get to your p-values. If you're dealing with a one-tail test, your p-values would be between a 0.01 and a 0.02. Or, since you could be dealing with a two-tail test, you'd have to double that, and that's where the two values down here come from. So let's go back to our cola problem. Here we have our 10 cola drinkers or testers. We have the data. If you enter your data into your first list and do your one variable stats on it, you get your average and you get your standard deviation. We can then use our t-statistic formula, taking our mean, which is our 2.0 or 1.02, minus our mu, which is 0. That's our null hypothesis, and that's what we had said before, over our standard deviation, which was the 1.9 or 1.196, over the square root of our n, which is our sample size. We type the top in, we type the bottom in, we divide the two, and we get a 2.7. Now, we had said before that we expected to have sweetness loss, so our alternative hypothesis was greater than, so it's a one-tail test. So we take our degrees of freedom of 9, go across to the 2.7, go down to our one-tail test. Our chart tells us it's going to be between a 0.01 and a 0.02 for our p-value. Now, since both of these values, and we know p is in between these two, is smaller than our significance level of 0.05, since both of these are smaller than that, we're going to then reject your null hypothesis. Now, we can also use your calculator to do this for you. So on your calculator, there's a couple ways you can do it. You can enter your data into list 1 and figure out your mean and standard deviation, and then just enter that in here. If you want to, you could put your data into list 1. When you go to your t-test, instead of having it on stats, you'd arrow to the left and hit data. If you had your data in list 1, your mu would be 0, your data is here in list 1, and you have a greater than because we're assuming we have sweetness loss, then you can go down to calculate. But if you don't want to have to worry about changing this back and forth, then you just want to go ahead and put your data in list 1, do your one variable stats, and then go ahead and enter your data. So if you enter your statistics you get from your one variable stats, you'd plug in your null hypothesis, which is 0 for this problem, your mean, your standard deviation, your sample size, and we were looking for your alternative hypothesis to be greater than. So then we go down and we hit calculate, and then we end up getting our answer. Now, as we look at this here, tells us our null hypothesis, tells us our t-statistic, tells us our p-value, and then it just repeats our standard deviation and our mean and our sample size. Now, our p-value here, once again, is what we want to look at to determine whether to reject or fail to reject. And if our p-value, once again, is smaller than alpha, and remember for this problem here, our alpha was at 5% or 0.05. Since this is smaller than that, yes, we would reject your null hypothesis. Using your t-test on your calculator is how I would encourage you to go ahead and do this problem versus doing it by hand. If you want to do one or two by hand to kind of get the idea of how it's done, that's fine, but then use your calculator. So now let's go back to the red wine problem. Our null hypothesis is 0. We're assuming it's going to help the polyphenols in the blood, so we're going to say it's greater than 0. Our sample average was 5.5. Our standard deviation from our sample is 2.517. We could go ahead and do the t-statistic by hand, but let's go ahead and use our calculator. So let's go back to stat, arrow to the left to test, down to t-test. Enter your statistics. Enter everything just like we have here. Then you're going to hit calculate. And then you're going to get this. But we know we have a problem here, because when you look at your p-value, you get 8 something, and you know that your p-value always has to be between 1 and 0. Well, it is really between 1 and 0. If you look at the very end, you have times e to the negative 5, which really means it's scientific notation. You got to take your decimal point where it is right here after the first 8, move it 5 places to the left. So it's really a 0.0000887. So it's a very, very tiny p-value. So here's your p-value written out. Since our p-value is definitely very, very small, we would reject your null hypothesis that there is no difference. So we would say it is statistically significant that the polyphenols on average increase with the drinking of your red wine. So when it's statistically significant, it's too large of a change to be due to chance. Let's go ahead and consider our matched pairs and how that works with our T procedure. A matched pairs situation could be before and after treatment, or pre-test, post-test. It could be where you're matching people up in general, which are similar according to age and gender and education and social status, and you're comparing those two people, looking at their differences. Or you could be comparing just your twins and trying to eliminate the effects of some of the variables by comparing the twins. Now, for the most part, we're looking at the difference between the two groups, the first group to the second group, the before to the after. So we're going to do some looking at the data from the first, we're going to look at the data from the second, and we're going to subtract the two, looking at the difference. So when you're looking at the difference, you should take the first one minus the second one, and you want that difference to be 0, because you're assuming there is no difference between the two groups. And if two things are identical and you subtract, you get 0. Your alternative hypothesis It's going to be, well, that the difference is greater than zero, or in some situations it could be that the difference is less than zero, or it may be in some situations that you know it's just different than zero. And then you go about doing your one sample t-test. So let's take a look at that cola problem. It's really a before and after storage. The sweetness before storage compared to the sweetness after storage. And here we would be looking at the differences, the sweetness lost from before storage to after storage. So this one here we would say it had 2 sweetness points lost. This one here lost zero point 0.4 sweetness points, and so on. Now, we really did this problem before, so we don't have to redo everything, but it's really following the same process. So for people who are caffeine dependent, if they're deprived of all caffeine foods and drinks, and then just receive a pill, where sometimes the pill has caffeine and sometimes it's just a placebo pill with no caffeine, we can go then ahead and decide if caffeine does affect depression levels or the lack of it. So we have our 11 subjects. Here we have their measurement of depression with caffeine. Here we have their measurement of depression without caffeine, the placebo pill. And then we have that for the second one and the third one and so on. Over here, we're looking at the differences. We're taking our placebo and we're subtracting the caffeine. So the 16 minus the 5 is our 11, or the 23 minus the 5 is our 18. All we really want to do is compare and work with the purple stuff over here. We need to see if it's normal. Well, if we make a histogram of this, we get this one here. It's somewhat normal. It's definitely not perfectly normal, but not extremely different than normal either. So we're okay using RT procedures. So if you want, you could go ahead and type these purple highlighted numbers into your list 1 of your calculator and do your one variable stats. When you do that, you would end up getting your mean to be a 7.36, your standard deviation being a 6.92. Our degrees of freedom is going to be 10 because we have 11 subjects, so it's 11 minus 1, which is 10. Now, we're assuming that there is no difference for our null hypothesis, so our difference between them is going to be 0. Your alternative hypothesis is that there's going to be an increase in depression. So we would expect it to be greater than 0. So we can go ahead and plug in your mean, your mu, your standard deviation, your sample size. We get our t-value. Using table C in the back of your book, you would end up getting it to be in row 10 going across, to be between these right here, so you know your p-value when you go down is between these here. Now that's if you're doing it by hand, but let's go ahead and type all this into our calculator. So let's go ahead and go back to our t-test, enter our data. We can then go ahead and calculate this. And we get a p-value that is pretty small. It's 0.002. Doing it by hand, we knew it was also fairly small. And since your p-value is really small, we're going to say that we reject our null hypothesis, that there is no difference between when they have caffeine and don't for our depression. So therefore, we would be finding evidence that a lack of caffeine does increase our depression levels.